good afternoon for everyone. First, I would like very happy that the room is full. Unfortunately, some of you of our project members that lives in São Paulo, they could not be here. There's Kalin Coutinho, Professor Ataalpa. Also, there's a few members more. There's some of the students are just arrived, but they might reach São Carlos on that night or someone's tomorrow, okay, because it's almost impossible to get out of São Paulo at the present moment, okay. First of all, I would like to invite our director, Professor Manuel Carrilho, to open our workshop.
Thank you, Juarez. Good afternoon, everybody. It's a great pleasure for me to open the fourth workshop from Center for Innovation New Energies. It's the fourth workshop, if I'm not mistaken, and you guys have a deep program in machine learning. So I'm very excited that the Institute of Chemistry of São Carlos is a partner and helps Professor Juarez to host this Center for Engineering. Is a project that is supported by FAPESP and by Shell, and we do our best to help the center. And I'm glad to see here the Vice Director, Hamilton Varela, also supporting this initiative. So with that, I'm very excited to later on see the lecture from Professor Osvaldo N, and a friend of a long date. And I think, as we were discussing here, the artificial intelligence is something that's going to dominate our everyday life, and it's better that we start getting acquainted to that as soon as possible. And Juarez is doing a great job in this aspect. So our house is open for you, for your center, and we would like to extend the congratulations for all your team and all team members from all the other centers. Thank you.
Then this time we also have the pleasure to have you with us here, Professor Rubens Marcial Filho. He's the director of the CINE, the Center for Innovation and on New Energy. Rubens, I'd just like to.
Good afternoon, everybody. I'm very happy to be here to learn a little bit about the application of artificial intelligence in new materials. That, as was mentioned, it's going to be not only a very hot topic in materials, but in all sciences. And I would like to welcome all of you for this new workshop organized by Division 4 of our center. I would like to thank you for the Chemistry Institute of USP for all the support that's given for Division 4, and for the other effort of Juarez in the excellent job, and they bring several students and invite all the divisions to be part of this workshop. That's quite important activity in the integration of our center. So I'm very much interested to learn how can we see things that appears to be in the future, but it's coming very quickly for our reality. Thanks very much, Juarez. Congratulations.
Thanks. Okay. Thanks for everyone. Okay, our program for these 5 days is basically to show here, as also there's outside too. Basically, today you're going to have 2 invited talks, basically for their specialists that work in machine learning for several years, while we are just starting. This is why we invite them here for us to teach a bit for us a bit too. Tomorrow we're going to have the talks by the students, and also post a section for all the members from the project, and also for some invited guests that will take part in our workshop. And then the remaining 3 days are dedicated to the hands-on on the Python and also machine learning application material science. This also will be in charge Marcos Quiles and also Ronaldo. Ronaldo is from the Federal University of ABC, and Marcos Quiles are from the UniFesp, from São José dos Campos, and both of them are specialists who work on computational materials, computational science, focused on machine learning applications. And we will try to combine our efforts in quantum chemistry with computational science. And then we expect that these 3 days of hands-on will provide for the students a background that they can use further for applications on their projects and so on. And also for the ones that comes that for external participants from the projects is an opportunity also to build up collaborations within the project and so on. Okay, I'm very happy that everyone is here. Now we move our first invite talk. basically, we are, as we mentioned before, we are just started. But I just started this project with the machine learning applications 2 years, maybe 1.5 years before, and then that topic we chose for this particular workshop because we believe that's very important. We have to move faster to recover time, and then we decided to invite Professor Osvaldo N Oliveira Jr. He is from the Institute of Physics of São Carlos. We have known him for quite a long time, but he's one of the here in São Carlos that work on the machine learning applications in combined material science for many years already, and about also the linguistics too. He is a full professor in the Institute of Physics, CINE-CMSC 1A for CINE-CMSC, and a well-recognized scientist here in our region, also in Brazil. And then it's a very, great pleasure to have you here, okay, to talk for us about the future of material science with artificial intelligence.
So, thank you very much, Juarez. It's a pleasure being here at the Institute, which is our sister institute, and the place where I did most of my, or almost all of my undergraduate studies. In those times, physics, we had a joint institute, physics and chemistry, and all the undergraduate classes were taken here. So it's always very nice to be back. The topic I chose to talk to you about today is very broad. I'm not going to any specific details of machine learning or artificial intelligence, but just to give you an overview of what is to come in the near future or perhaps midterm. This is the outline of the presentation. So I'll discuss the different paradigms of how humans through history have generated knowledge and acquired and transferred knowledge. And then I'll make a connection with what I believe can happen with artificial intelligence very soon. And last but not least, I'll make the connection between artificial intelligence and material science and chemistry. So the first, if you look at how humans generated knowledge over the years, or over history, we started with the first paradigm during ancient Greece, where knowledge was acquired and transferred via descriptions and empirical studies. We did not have, humans did not have models to explain the data or the results. These only came over 2,000 years later during the Renaissance with Newton, Galileo, and all their followers, in which we had theory or mathematical models to explain experimental results. So a few centuries later on, we had the third paradigm in which you could build knowledge by using theory, experiment, and simulations, computer simulations, which means that we had to wait for the computers to be invented to have this third paradigm. And then only a few decades later, we had the fourth paradigm at the end of last century, in which we could build knowledge by putting together experiments, theory, computer simulations, and now big data, because there was already so much data available, and humans found ways of getting information from this amount of data, this tremendous amount of data, and transforming information into knowledge. So in these first four paradigms, regardless of how sophisticated the methods were, the instruments were, or the theories, at the end of the day, every single piece of knowledge was generated by a human. Machines themselves do not generate knowledge today. Very soon, my guess is that the machines will be able to generate knowledge. They will be able to do intellectual work in an independent way. This is what I call the fifth paradigm, where you have knowledge generated automatically by the machines. how this is going to happen? This is probably going to happen with the convergence of two big movements. On the left-hand side of this slide, you have the big data movement. So you have a lot of data, preferably machine readable. Preferably machine readable because the machines today cannot read. I cannot ask a computer or an intelligent system to go and read a book and come back with answers. I cannot do it. Machines cannot read yet. And therefore, in this movement, the data should be preferably machine readable. And then use machine learning to transform information to knowledge from this data. Oh, this is the big data movement. Obviously, this is a very generic concept and explanation, very simplified way, but it's more or less explains how big data works. The movement on the right-hand side is the complementary movement, which is to teach how the machines will learn, or to teach the machines how to read and interpret text. You can call it natural language processing or other names. Perhaps natural language processing would be the best name for this second movement. The approach is very similar to the first, the big data movement, in which you get a lot of data and then you use machine learning to teach the machine to read. The difference now is that the data is text. It could be spoken text or could be written text. Today, we already use a number of tools and systems which work with this paradigm here. Examples, perhaps the most famous ones are machine translators, which use this sort of method, and voice recognition systems, and all the intelligent searching engines. In all of those cases, you use natural language processing. So you see, because humans acquire knowledge via language, either natural language, Portuguese, English, Chinese, French, or whatever, and mathematical formalisms. So as we acquire knowledge through this, through language, this movement here is absolutely essential. Why is this so important? Because whereas the movement on the left, the big data, is completely language independent, on the right-hand side, we have a movement which does depend on the language, which means that for Portuguese, we should be in a, say, in a good position to make contributions. And therefore, we should invest a lot on this area. You may see that I use two different ellipses to represent machine learning. One is a solid one, the other one is a dashed broken line. Because with machine learning, you can do essentially two types of tasks. One is classification. And for classification, machine learning has been proven beyond doubt. If the amount of data you have available is sufficient and the processing power as well, you can always do right classifications, better than the humans. The examples we have today are facial recognition, for instance. Machine translation is another example. And many other clinical diagnosis, for instance, with radiology images, in which it's proven beyond doubt that the computer systems are already better than the humans. So machine learning for classification is, I mean, almost problem solved conceptually. So if we have sufficient data, and obviously good quality data, and we have enough processing power, we can do classification better than the humans. However, if what you are going to solve, the problem you're going to solve is to answer questions like why, how, what, that you need interpretation, then machine learning is not as good as the humans are now. So there is tremendous amount of research now on this area, machine learning for explanation, because once you get there, we'll be able to teach the machines to read. Because that's one of the major limitations of artificial intelligence, is that the machines cannot interpret. And the reason is because it's very hard to do machine learning for interpretation tasks. Some researchers have mentioned that machine learning has been more successful in hard sciences and engineering and not so much in social sciences, humanities. Well, that's very easy to explain, because the phenomena and problems that you deal with in sociology or social sciences and humanities, they are usually much more difficult to address. You have samples which are not as well defined. Usually you do not have statistics. By the way, that's a nice place to be to make this comparison. When we're doing statistics in physics and chemistry, the statistics works, for instance, for a gas or a material, because we have Avogadro number of particles. So we can do statistics at very high accuracy, because you have 6 times 10 to the 23 of components in our system. But if you're doing this, for instance, with social behavior, the number of humans we have now is only 10 to the 9. So even if you use data for all the humans, you're still far away from the Avogadro number. It's much more difficult to get the statistics of high quality so that you can be sure about the answers. So then, with these limitations, it's possible, or it's likely that we'll still have to wait for a decade, 2 decades, before we get the machines generating knowledge, because we have to overcome these limitations. And what are the requirements for getting there? First, you need a lot of text and understand, or we need to be able to process text. Not only process as the computers do today, but also with this machine learning that applies to do explanation or interpretation tasks. And then you need data from all different types of experiments, simulations, theory, and so on. So quality data is essential for making this intelligent system. We need Internet of Things, because the machines, the intelligent machines, will need to have things connected so that it can acquire data, process this data, and respond accordingly. So this is also another need. And obviously, machine learning methods. That's one interesting thing. The most successful paradigm for machine learning today is deep learning. And the victory of machine learning is actually a defeat for the human race, because deep learning is by far not the most clever ways that humans created for machine learning. Because deep learning, at the end of the day, means that you are doing many things at brute force. But it works. And it has been the best paradigm so far. I will give, just by way of illustration, an example of computer assisted diagnosis, so that we have convergence of different types of data. So materials discovery, now coming, and how about material science on this, or chemistry for this matter? Material science or chemistry has a relationship with artificial intelligence, which is a two-way relationship. On one hand, because you need a lot of data for the intelligent systems, you need material science, you need chemistry, you need physics, because you need sensors, you need actuators. So researchers like we are, I guess almost everybody here is physicists, chemists, engineers, so hard science or material scientists. If we are material scientists, we can help the intelligent systems by providing the devices and the data for the intelligent systems. On the other hand, you can now benefit from artificial intelligence to help us produce better materials. So this area of materials discovery and design has been very hot, and I'm going to show you some data over recent years, in which you try to use big data plus machine learning to guess or to predict properties of materials and predict new materials. So we had, at the end of last year, we had a forum at this journal, ICS Applied Materials and Interfaces, which was co-edited by me and Professor Gustavo Dalpian, in which a number of papers were published on this particular topic. And you can read here, this is a new paradigm of all sorts of materials applications. It does not apply to a specific class of material. It can be used to any class. So just a sample of some of the papers that have been published in this special issue, in this forum issue. So there was work on autonomous molecular design of materials, and then use high throughput equilibrium analysis, and that's an interesting thing. You can do high throughput experiments. You can also do high throughput calculations, theoretical calculations. For instance, density functional theory can be done now with this high throughput concept. So we had a lot of data generated by the simulations altogether. And so just to summarize, machine learning, material science, and chemistry or physics, these terms can be used depending on the audience. If I'm in a chemistry institute, I can use chemistry. If I'm in a material science department, I can use material science. If it's a physics department, I can use physics, because it doesn't really make any difference whether it's chemistry, physics, material science. So you can use materials, these concepts and methods of material discovery for identifying new compounds, for instance, using genetic algorithms. You can do drug design. So drug design is now entirely dominated by machine learning and big data. And computational biology is another area in which has benefited a lot from machine learning. And then these are for materials discovery, but you can also use machine learning for analyzing data. And that's another very interesting aspect of this interrelationship between artificial intelligence and material science, chemistry, physics. Because you can use machine learning to analyze data. When you have a lot of data, you can use machine learning, especially to do pattern recognition. That's something which can bring us to very basic principles. We all have our mothers saying that they know us better than anybody else. Why is that so? Is there anything genetic about it? There may be, but probably, or most certainly, it's not the main factor. The main factor is that our mothers have, better than anybody else, chances to watch us, see us acting. So they know us. They establish patterns of how we behave. Now, this is done by the machines, which gather data from us more and more and can know us better than anybody else. You may say that there are ethical problems there. We know it. And this has been discussed a lot with the social media or those apps getting information about us without us knowing. So this brings a lot of ethical issues. But the reality is that we now have machines having so much data about people, about things, that they can establish patterns. And that's something interesting for audiences of physicists and chemists, or engineers for that matter. I don't know whether there is anyone in the audience who was my student in the grad. I don't know, probably, yeah. But when you teach physics or chemistry, You get a textbook, and at the end of the textbook, we have hundreds of exercises or problems to be solved. We may get the impression that real life is like that you have a problem, you can use a model, you can use equations and solve those problems. But not in real life. In real life, most of the problems we have to deal with cannot be solved with a theoretical model or equation. We need to classify. When you go to a doctor, the doctor has no way, the doctor cannot establish a model of your health and try to solve the problem. The doctor will classify you. Therefore, many problems that we have to deal with in our real life are classification problems. And if machine learning is so good for classifications, it goes without saying that machine learning will be very effective. And that's what happens with pattern recognition, image analysis, and so on. Some examples of achievements that have been made in the literature on machine learning and big data used in chemistry or material science. In some cases, you may see that it may change the way we choose the scientific problems we want to address. Because, for instance, if you work on organic photovoltaics, it doesn't make sense for you to start looking for new materials without looking what this consortium of researchers have. Look at that. They have a library of over 200,000 compounds, organic compounds, which have been screened and studied for photovoltaics. And they calculate for these 200,000 compounds the HOMO and LUMO levels with an accuracy of 0.15 EV, which is it's very close to what we can get with DFT. So the best theoretical method that we have invented so far is matched with this machine learning system. This other example is also very interesting for chemistry. A few decades ago, the task to try and predict the result of a reaction in organic chemistry was considered mission impossible. They tried to do intelligent systems, but there are so many factors that could not be accounted for, could not be considered by the systems in those times. The processing power was completely different. The amount of data available was completely different. Now you can do it. You see, this group of scientists from the US, they could predict with 97% accuracy the outcome of chemical reactions in organic synthesis. I showed two examples of papers published in other countries. It's my pleasure now to show something which was made in Brazil, in São Carlos. I don't know whether Daniel Cassar is here. Oh, nice to meet you. It's not going to be a spoiler because that's the only slide that I'm going to show. And I won't be able to explain how things are done, so you can do it later on. This is the work that Daniel and Professor André Carvalho here from Computer Science Department in USP and Professor Garzanot from UFSC, in which they had a machine learning system which can predict with the same accuracy of the dispersion of the data you find in the literature, the glass transition temperature of over 50,000 glasses. I mean, if you are working on this area, if you're thinking about working on this area, it doesn't make any sense whatsoever to start without talking to them. Because you see, you cannot compete with, with a team which can predict properties of 55,000 glasses at once. So you see, even for us to choose our scientific or technological problems, we have to see what's available in artificial intelligence for that particular application. You cannot just go without looking what is in there. Now, you may say that there is this crazy guy who just happened to work on natural language processing and being a physics professor. So this guy may have a vested interest in trying to promote the area. So he may come and say that you can put, as I showed in this second or third slide, you can put natural language processing side by side with other areas. But you see, now this is an example of a paper published a few years ago in Chemistry of Materials by a group in the US, led by Professor Elsa Olivetti, in which they use just that, natural language processing, to mine the literature and trying to get information from thousands of papers, in that particular case related to synthesis. So they wanted to get insights about results of synthesis, is going with a crawler working on the literature. Because there are thousands of papers in almost any topic, you can only do it today with automated tools. So it's now the time that this other area, which had nothing to do with hard sciences and engineering, natural language processing, it's now the time you have to consider this as well. We have to bring into our framework of research. There have been some, or there are some tools to help you mine data for the literature. There is a group in Ribeirão Preto led by Professor Gessiane Porto working on patents. They have just published a paper in one of the Nature journals on this. Our group itself, I didn't bring this slide, but I can give you the reference later on. We published a few years ago a system which does automated surveys. So you get an area, and then from keywords on that area, you search the Web of Science, get all the papers. So we got over 12,000 papers on a specific field, and then we have a network representing that particular field with all the connections and so on and so forth. So we combine network science and natural language processing to trying to do a semi-automated survey. What's the limitation of our work? The limitation is a very simple one. With machine learning, we can do classification, but we cannot interpret. And so we have the field classified in terms and areas, but we cannot establish a hierarchy as a human would do when you write a survey. So that's a limitation of our work, or a limitation of any type of work like this in the literature, because machine learning can still not do interpretation. So what's going on in the literature? Over the last few years, you can see here, this year, so 2011, this is 2019, and this is the number of papers published in the Web of Science, indexed in the Web of Science, with these keywords, machine learning and chemistry of materials discovery. You see here, over the last 2 years, 2018, 2019, there were more papers than all the previous years. So this means that anyone who started doing a survey in 2016 or 17, as in our case, we lost 1 year of entire work on a review paper, which was not accepted. And when we decided to change what the referees had asked us, just too late, because we had to redo everything again. And so we put in archive there. I put the reference there. It's a shame, 1 year of work lost, but that's life. It shows how critical it is to choose what you're going to do. So if you're doing a survey on this, so that everything happened over the two last years. And now, an interesting thing in this plot is to see where the papers come from. Mostly from the US, and the reason is simple. The US launched a few years ago those initiatives called materials genome. You may have heard of that. And there was a similar initiative in Europe. There are plenty of these initiatives in China, but the papers have not surfaced yet. First, because they are applying for engineering applications, in many cases published in Chinese, so they are not appearing in the Web of Science. And in the first few years of any given field, it's a tremendous advantage of the English-speaking countries who can tell the story. Who can, not with a lot of data, not a lot of results, but showing the way. So the familiarity and expertise in a language helps a lot. And that's why you see, you have the US, you have England, you have even Australia there. We don't see Brazil. And I hope that with initiatives like you have in your center now, we can put Brazil in the map in a few years. But this is going to change dramatically once China starts publishing. Because if you get material science or nanotechnology, for instance, China today already publishes almost twice as much as the US. So this is going to be shown very shortly because they are working a lot on this area. Now, you may say, and how about the connection with material science in real terms of research? I'm going to give a few examples of sensing and biosensing just because that's something that we do in our group of collaborators. Biosensing, by the way, is one of very strong areas in USP at the University of São Paulo. The University of São Paulo is very strong in biosensing because we have groups, including the directors group, working on biosensing, so we are very strong on that. And with a biosensor, why machine learning and artificial intelligence may be connected with sensing and biosensing. The connection appears because machine learning can be used to analyze data. We are still not in a position to use machine learning for materials discovery in biosensing, not yet, but probably will be in a short while, once the number of biosensors increase as it has been increasing over the last few decades. So it's probable that we are going to have machine learning applied for materials discovery for biosensors as well. But a biosensor is a device in which you have a bioactive layer here with whatever biomolecule to recognize specifically the analyte. So it may be enzymes to detect their analytes or antibodies to detect their antigens or vice versa and so on. But because these biomolecules usually cannot survive for a long time, or they cannot be active for a long time, if they are just spread on a surface, you may need a matrix. So working on different types of matrices is something which many groups do. And then you may need to amplify the signal. The signal could be optical, electrical, electrochemical, so on. And the other examples of biosensors, I'm going to show an example of biosensor for cancer diagnosis in a moment. But the other application, which is very connected, perhaps one of the first applications of artificial intelligence for sensing, is with the electronic tongues. An electronic tongue mimics what our tongue does, because whatever we taste is just a combination of basic tastes. So when we are drinking coffee, for instance, or wine, we are not detecting any specific chemical substance. We are not detecting caffeine, for instance, or the polyphenols in wine. We are detecting a combination, so our brain receives a signal, which is a combination of 5 basic tastes. So salty, sour, sweet, bitter, and umami. So these are the 5 basic tastes. So because it's not selective, or it has a what we call global selectivity, for each liquid that's tasted, there is a pattern, like a fingerprint, of that particular liquid. And to build this, rather than using just one sensor, you may use several sensors, 4 or 5 sensors. And you can even use biosensors to increase the selectivity. The electronic tank that has been studied in Brazil for almost 2 decades now is very sensitive. For salt, for instance, is 10,000 times more sensitive than the human tank. It's so sensitive that you can distinguish between wines. So if you have wines which have the same grape, the same producer in different vintages, or the same vintage, the same grape, different producers, and so on. So you can always distinguish one liquid from the other. But the question arises as, can you use an electronic tank to say something which is delicious or not? Indeed, you can. You can teach your system what's good and bad in terms of taste based on the human perception. So this is a result done now 13 years ago. The artificial intelligence expert was Professor André Carvalho, the same collaborator for Daniel Cassar. André Carvalho is around for years working on these applications. And so here, the results are for coffee. So different types of coffee were tasted by professionals, humans, from the Brazilian Association for the Coffee Industry. And they assigned scores for the coffee. So the increases on this direction on the x-axis. On the y-axis is the predictor score based on the data of the electronic tank. So we measured with impedance spectroscopy the electrical response of each coffee. And then we use artificial intelligence, different types of, or different methods of machine learning to do regression and establish the predicted scores. We use different machine learning methods. If you concentrate on the solid squares, you see a very high correlation. So the Pearson coefficient is 0.964. 1 would be full correlation. And therefore, you can predict the score of a coffee sample based on the data from the electronic tank. So you can actually teach the electronic tank what is good and bad. So I mentioned about results for biosensors. This is just a very recent result that we got. And the reason I'm showing this is because of its significance. So you may see from the press that prostate cancer is detected today by a combination of methods. The first one is blood test of biomarker, a protein called PSA. The problem with this test is that PSA is not very specific, is not specific for cancer. So you may have a high concentration of PSA, but it could be just an increase in the prostate or just prostatitis and not cancer. So that's why the doctor has also to do the touch test. And if there is any suspicion of cancer, you need to do a biopsy. You would be amazed to learn that 2/3 of the biopsies turn out to be negative. They were not necessary, but the doctors could not risk. A few years ago, doctors found another biomarker for prostate cancer, and this is very specific. It's called PCA3. PCA3 today is only detected with just those very sophisticated methods, which are expensive, and that's why you cannot find, in the health system, you cannot just go to a lab and ask to be tested for PCA3. That's what we did in collaboration with the Barretos Cancer Hospital, is to produce a biosensor which can detect PCA3. So far, we showed that we can detect, so here, you can see these are the analyte PCA3 in buffer, so we call synthetic samples. Red is negative, here is positive, and with increasing concentration. As you increase the concentration goes further away from the negative controls. And we can also detect in cells that were extracted from tumors, from prostate. So if the cell has no, if it's a tumor not of prostate cancer, we do not see the results. If it is, we can detect. We still haven't done this with urine, which would be the most important test. And we are hopeful that soon, if companies are interested, this type of test can be put into the national health system. Now, I promised to talk a little bit about a computer-assisted diagnosis system. This is a view graph of a general concept of how diagnosis is done today. Today, when you go to the doctor, so here you are, the patient, you show the doctor have reports, it could be your health records, electronic or written health records, clinical data of clinical analysis, blood tests, urine tests, whatever, images of whatever tests you made. And then the doctor gets all this information using his or her experience, and it jumps to the diagnosis. In the future, or in some cases the future is now, so this is already being done in many places. What the doctors will have at their disposals is a repository of data from thousands, perhaps in the future, millions of patients. And then the system will do a number of transformations, pre-processing, whatever, because you may have data from different natures. You see, in the future, we should combine data from text, from scientific data, plots, spectra, measurements of conductance or whatever, and images. We should put them all in the same pot. And for this, you need a lot of computer simulations, treatment, and so on. And at the end, data mining, machine learning to get to this, to the diagnosis. That's one thing which is interesting to mention. For us, scientists, the type of data matters a lot. If you get a spectrum from nuclear magnetic resonance, unless you know the area, you cannot interpret it, you cannot use it. If it's from optical spectrum, the same, electrical data, the same. Not for the machines. The machines, for them, data is data. If the task is to classify, the only thing you have to provide the machine with is what your input data. If it's not supervised, you can just put the data there and see whether it can cluster. And if it's supervised learning, you can establish the classes and then teach the system how to classify. Data is data. It doesn't really matter whether it's text or whether it's scientific data, images. By the way, that's another twist of history in science that's a very nice one for us. We have good stories about São Carlos because we have a very high concentration of people working in different areas, and this is possible. When you are doing clustering of sensing data or biosensing data, you may use several methods that are available in the literature. For biosensing data, the best one is a technique called interactive document mapping. This is a method that was created for text. not for sensing data. And this technique was created in our computer science department here at São Carlos. And it's the best method. We tried all methods available in the literature, and this is the best one for biosensing. And it was conceived for text, not to classify sensing data. I repeat the mantra, data is data. It doesn't really matter for the computer or for the computational system where the data comes from, what's the nature of the data. Just summarize the sort of conversion of technology that we need. We need the e-science and computer science work, as I've been talking. But to have meaningful results, we still have to understand how things work. So we need all of those things in nanoscience and chemistry and physics. So we still have to do it. Obviously, once the intelligent machines are made, the machines will be able to do by themselves. But before we get there, we need to understand. That's another way of showing how, this is the paper never published, how we see the interconnection between material science and materials discovery and machine learning. So you see, with material science, as I mentioned before, you get data, a lot of data, which feed the machine learning systems to do basically two things: to do material discovery here, or to solve problems in chemistry. We call chemistry here because this paper was meant for a chemistry journal, so we could choose we could change the term there. To finish, I make two statements here. First one is that machine learning will change this landscape of science technology. I mean, I think I wrote this sentence a few years ago when perhaps this was not expected. But now I think everybody knows it, so not a big deal. The other statement is a little bit more, a little bit bolder, which is, in a few decades, most intellectual tasks, and I would, based on my last lecture on this, I should have done it already, but I forgot. I will remove this most here and change it for all intellectual tasks will be better performed by machines, better than humans. Because I cannot think of any intellectual task which will be better performed by humans compared to what the machines will be able to do. We have to discuss this. And for the young people here, a provocation. You are trying to solve a problem. You have your project of MSc, PhD, postdoc. Have you ever asked yourself how an intelligent machine would solve the same problem? That's one thing. And second, are you sure the problem cannot be solved in other ways and you don't even have to perform your project? That's an important point, because for many years we expected the robots to be like us, to solve problems like we do. But that's not what turned out. The way the machines solve problems may be entirely different. And that's very simple to explain, because the machines can do things that we can never do. Just one example. You may have heard of this IBM computer, Watson, which does natural language processing. This computer can process close to 1 million books in a second. So the way it is going to solve problems is going to be very different from the way we do, because you can never get anywhere close. I'm a fast reader, but 1 million books in a second, not possible. So the machines will solve problems in very different ways than we do. In natural language processing, for years and years, I made the mistake to think that a machine will have to understand, to interpret the text to solve the problems. And we now know this may not be needed. For machine translation, for instance, which has improved a lot, this has not been needed. Because you see, we have a very efficient machine translation today, and the machine translating system does not understand a word, a single word of what is there. The only thing that it does is get a tremendous amount of text in one language, and the translation of those pieces of text in the other language, and then just use machine learning to learn how to translate. And that's it. There is no semantic treatment, nothing of very intellectual nature that we could call it in what the machine translation system does. And yet, it's very efficient. With this, I finished. There is a long list of collaborators of some of the work that I showed, and the list of sponsors. And then, last but not least, you are all invited to our Brazilian MRS meeting in September, late August, early September. Thank you very much. You have, he needs the microphone, I guess. Yeah.
Machine learning is depends on the existence of large databases. What is the size limit of database? What is the size limit of database where machine learning is reliable?
A very good question. Even though I'm not an expert on using machine learning, but from what I have seen is that it depends very much on the application. So there is, depending on the method that you use and the problem you are going to solve, you may not need a lot of data. For deep learning, for sure, you need a lot of data, but not for other methods. So the amount of data may not be that big, and I don't think that it's possible to establish a limit for a general limit. The limit or the minimum requirement will depend on the application. One thing which is important is that with the machine learning method, usually once you start increasing the amount of data, and your performance increases until it reaches a plateau. It could be 1 if you can solve the problem, or it can be below 1, and therefore it doesn't really matter that you put more and more data, the performance does not improve. But with deep learning, experiments have been done in which, as you increase the amount of data, the performance always increases. The performance always increases with deep learning. Therefore, it's really promising because you may have more and more efficient systems as you increase the amount of data.
Osvaldo, thanks very much for a very nice talk. Let me just see. Nowadays, you use, for instance, artificial neural networks to deal with data to get some correlation or some interpretation. When you don't have precise information, you go to the fuse theory-based languages and then put together to understand how you organize, how do you think that you can put this kind of a treatment with the natural language learning to build up a quicker solver, for instance, or tool to identify or to search for new materials or so on.
Yeah, because I think materials discovery and other applications are still at a, say, I would say embryonic stage. Everything is done like craft. So you tune your algorithms, you choose the methods for a given application. In many cases, what scientists do, they try several algorithms to see which one is the best. And I don't think there is any rule of thumb to predict which is going to be the best approach. I mean, I think now with more and more results being gathered, very soon we're going to have, for some classes of problems, you may have what would be the best algorithms to use or the best methods. But so far, this is always done in case by case. So we cannot predict beforehand which would be the best method to use for a particular application.
Thank you very much for this very inspiring lecture. And of course, I was astonished by your last sentence that you said that most or all intellectual problems can be solved by machines. And in particularly yesterday, I finished a great novel by Lev Tolstoy. It's called Anna Karenina. And I was extremely sad because she killed herself at the end. So I took 5 weeks to read this book. I'm sure that a computer can read it much faster, as I said, a fraction of a second, but I wonder whether a computer can be sad at the end.
That's a very interesting. If you remember the sentence, here I say intellectual tasks, and I use this wording on purpose. I mean tasks. I'm not saying that the computers will behave like humans. The computers will perform the task. Will the computer understand how it is doing? It may not. Like a student who learn all the solutions of problems by heart, come and get maximum score, and if you ask him or her, he or she may not really have understood the topic, but if he or he knows all the solutions, and this may happen with the computer. So I'm always careful to say intellectual tasks. I'm not saying that the computers are going to be as creative. We don't know, because we don't really know what creativity is. What I mean is that computers will be able to create art in a way that we will not be able to distinguish just whether just created by computer or by a human. And that's, and many other examples.
Thank you, Shu. Very provocative and inspiring. And I was already puzzled in your first slide when you said that the future, the computer and the systems will be able to generate knowledge. What can men do to prevent that they generate knowledge and keep the knowledge for themselves, like the systems?
Well, that's very difficult to answer, and perhaps it's a high time we started discussing ethics of the intelligent systems. We need to do it. So I think that there must be a way to make sure that the machines will not just want to destroy us in the end when they notice that we are no longer needed. Because you see, the machines will be able to do it, almost everything. And so it may be, I can think of a case in which they say, oh, the humans are just getting in our way of doing nice things and can remove them. And the only way to avoid it is to put hurdles or limits in the intelligent systems. Because after all, like this generation of these young guys here, they are the ones who are going to build the intelligent machines. So it's up to you to put limits into the intelligent systems. Not for me, because I'll be too old. Yeah, but I mean, yeah, we have some control, but mind you, talking about control, have you ever thought that there are things created by humans which are no longer under our control? One thing, internet. Nobody is able to disconnect internet. Impossible. No group of men or women, no group of humans can disconnect internet. It's completely out of our control. And the same applies to the energy systems in some countries. You cannot simply disconnect the whole thing, even if you wish. Even if you are the president, even if you're a dictator, you cannot do it. So there are things that we created that are already outside our control. So the machines will be similar. Obviously, it's more dangerous because they will be clever.
I would like to thank the presentation. I would like to question about the science that we do now. In some years, a machine will do better, and all the science we do now will be obsolete. And I would like to know how we know that we are investing our time and resources in this kind of new technology in the right amount and not less or more.
That's a very important philosophical question. First, this will happen if we as individuals decide, especially in Brazil, that we have very little power compared to other countries. If we decide that we don't want to develop intelligent systems because we think it's bad, it's absolutely useless to make this decision, because it will happen. It is driven by economics. So this will happen. So we have to do the best we can to develop the intelligent system as well as we can, and with ethics. One thing. Second, we know that technology creates inequality. The more technology you have, the more unequal is our society. We have to deal with that. Because if we have inequality today, it's going to be much worse in the future. And it's not difficult to understand this. Because suppose that you want to distribute wealth. If the wealth you are going to distribute is money, you can come, take a lot of money and distribute to the whole population. Some people will use the money well, others will not. So in a few years' time, some people will be poor again without any money. But anyhow, you can distribute money because people can use money. However, if you want to distribute is the most important thing, which is not money but knowledge, that's not so easy. Suppose that I was to give a lecture in Japanese or in Chinese, with all my slides in Japanese and Chinese. I don't know, perhaps some of you may be able to grasp something, but most of you will not understand a thing. So you will not be able to acquire that knowledge. So distributing knowledge is much more difficult than distributing wealth. And there is nothing which is more unequal in a society than the amount of knowledge that the population have. So we have to think about it. And we have to think it scientifically. Because inequality today is always treated with ideology, not with knowledge, not with science. And we need to do it. That's the only way to address. So doing better and better science, we're going to improve our living standards as we are doing. So humans are living better than any other period in history. The population is increasing, birth mortality is decreasing, so on and so forth. So we are living the best of all the times. And this is just because we have science. In fact, the main reason, that's a good question. The 20th century saw more development than all the other centuries put together before. Why was that so? Why the 20th century was so special? What do you think? What would be the reason? Wars? What else? Which type of knowledge? The answer I get most frequently is wars. Then I remind the audience that before the 20th century, there have been many wars, bloody wars as in the 20th century, but with less technology, and we didn't see development. The main reason, I think, is that in the beginning of the 20th century, we deciphered the structure of matter. We finally understood how matter is structured, and this changed the whole thing. Then we can have computers, semiconductors, new drugs, so on, plastics. And that made the difference. So the 20th century was so special because we deciphered finally how matter works. So it is knowledge which brought us to the situation we have today. And this will not change with the intelligent systems. Obviously, after they take over in terms of intellectual tasks, we need to do other things. We need to find other ways of, we don't know what you're going to do, but, or you are going to do. I'll probably be dead, but you are going to be alive and you'll be seeing the intelligent machines doing everything which is intellectual. My pleasure.